The most general situation we can have for relative motion of two objects moving along the same axis can be expressed as we do here. Okay, so we're going to have some acceleration for the object, and that's going to be the second derivative of its position. We have the position of the object. This position is the position of the object at this time. This velocity is the velocity of the object at this time. This implies the quadratic relationship, and I'm not going to use a v naught or an x naught here because those quantities weren't given. And it might be confusing to use a v naught and an x naught when we got an x1i and all that stuff. So I just use b1 and c1. The derivative of this, of course, is this. So v1 of t is a1t plus b, derivative of this. And it follows then using the initial, or the given information about velocity. Well, we can see what follows, okay? We just plug in t10 for t, v1i for the velocity, and we can solve for b1. And then we can do similarly in this equation for c1 if we just use, if we just use t10 for the time and set that equal to x1i. We easily solve for c1, and then we can do the same thing for a second object. So, our functions in general will look like this, but if we have sufficient information, we can evaluate a1, b1, c1, a2, b2, c2. Then to answer the question of when they meet, well, obviously that occurs when x1 equals x2. So if this function equals this function, how do we solve for t? Because that's when they meet, of course. Well, we just bring everything over onto one side of the equation. The other side is going to equal 0, and we're going to apply the quadratic formula. It's no use to try to factor if this is real-world information. It'll never factor. If it does, it might be the first time in the age of the universe. But use the quadratic formula to solve. In general, we're going to get two parabolas. Another way I've drawn these parabolas, this one seems to open a little wider than this one, which means that there will be a time here where the two parabolas meet. And of course, this is a position versus time. And there'll be probably a time over here, because this one's going to go up faster than this one is. They'll intersect somewhere over here on the left. Now, those times might not be both in the domain of the function. For example, if you start these things at some instant, say at t equals 0, then the domain would consist of only t values that are greater than 0. The negative t values wouldn't apply, and any part of this parabola to the left of the x-axis would not apply. Then there might be some point at which the system ceases to move, or one object or another ceases to accelerate uniformly for one reason or another, and then that would restrict the domain. So there's no guarantee that in the first place there are solutions to this equation. The discriminant might be negative, and even if there are, there's no guarantee that either of those solutions is going to be in the domain of the function, although both might be.